close to the end already. Yeah, I guess quick announcements, just so we're all kind of on that same page. So next week, Monday there's no class, it's Memorial Day, so don't show up. We're only gonna have class on Wednesday. And then I think that's actually gonna be our last lecture. So I guess today is our second to last lecture. Next Wednesday will be our last lecture. I believe that's correct. And then after that, we'll do final presentation. So I'll make an announcement on Canvas about how that's gonna work, because we actually have too many groups to present all at once. So I'll make a poll, and then you guys can just volunteer to do a recorded one, or you can volunteer to present it to your class. And if we can't get a good breakdown, you're gonna get randomly assigned. Okay? Any questions about any of that? Okay. So, today, let me pull up the right screen. All right, what are we talking about today? So moving beyond splines and kernels. So we talked last time about some, let's say, more traditional machine learning approaches for classification. And we're going to start to delve into that a little bit more on some machine learning tools that we use for regular old regression, right? And so continuous variables. So splines, right? So this is like a semi-parametric approach that is functionally flexible. And you've got your kernels, which are powerful, non-parametric approaches for finding decision boundaries. And hopefully you guys have seen through some of the examples that the ability of these two models to kind of fit to very non-linear forms is actually pretty powerful, right? And these are both methods that, have the ability to fit to highly nonlinear data. But there are some other approaches that we're going to talk about today that have become a lot more popular than these two. And so, kind of why is that? So we are going to talk about neural networks today. And, for the size of the examples that we're doing, they may look pretty similar to these types of things, but one of the big benefits and one of the really big reasons why neural networks has become such a staple in machine learning is they are powerful tools that scale very well. And what does that mean? So that means I can handle more. Okay, we're going to start using machine learning lingo, even though it doesn't really mean anything. So more features. If you hear people talking about features, it's because they're related to machine learning, but it's just explanatory variables, right? So you have more So both splines and kernels, splines, you may have some difficulty scaling up on the more feature side of things, and then kernels, you may have some more difficulty scaling up on the more data side of things. And so those are kind of fundamental drawbacks just with the way that the computational complexity is regarding those two models, that a lot of neural networks and other sort of adjacent machine learning tools have been kind of built to overcome.
So are we talking about all machine learning tools when you say?
No, I'm kind of talking about neural networks and things like neural networks,
Okay.
because actually, as much as machine learning wants to lay claim to, like linear regression and logistic regression, these are like topics that you would learn in a machine learning class, but it's just regression, right? Yeah, so I would say don't worry too much about getting caught up in what falls into econometrics versus machine learning versus statistics. Let's just learn the tools and see what that can get us. Okay, any other questions about that?
Are we gonna learn what neural networks, what that means?
Yep. That's pretty much all we're talking about today. The neural networks is actually kind of derived from the way that we think about neurons and how they work in a biological system. So actually, neurons in your nervous system and in your brain are connected to one another, and they transmit information from one neuron to another. And we are going to reorient the way that we've been talking about some of the models that we've done to think about it in that way. And yeah, it very much is kind of a replication of a biological neural network. So, okay. I feel like I'm talking in mystery and in code, so let's just dive into it, okay? So, there's a bunch of lingo that I'm going to write out, and we're going to hit definitions of these things as we go through the lecture. But I'm just going to write them out now so that we don't forget, and if I miss anything, you guys can remind me. Okay, so machine learning lingo. So we have tensor, layers, weights, loss function, /score, optimizer, and a perceptron. Okay. So let me start with a simple example. This is probably one of the simplest neural networks that you could build. So let's take an input 1 and an input 2, and these two inputs will combine with some weight. We'll call it weight W11, W12, into something like this. Okay? So inputs affected by some weight, resulting in some kind of output we call L. So this function might look something like this: I1 and I2, right? And I will write this out like W11I1 plus W12I2 is equal to L. Does this look like anything familiar? This equation? No, not at all. Okay. What about if I wrote it like this? How about now? So this is a neural network representation of a linear regression. Okay? Pretty straightforward, right? Neural networks, actually not that complicated. So we've kind of reoriented to think about it in this kind of diagram, but essentially you have inputs that relate to some output. The weights are calibrated in a certain way, right? In order to do what? What are we doing?
Represent reality.
Well, mathematically, more specifically, in a linear regression.
Predict?
How do we estimate the betas again? Does anyone remember?
You estimate the trend line?
Yeah, and how do we estimate the trend line again? Are we, what are
You're
we
minimizing the
minimizing? Yes, minimizing the sum of all those errors, right? And so there's some procedure that we go through to figure out what the betas are. Similarly, right, there's some procedure that we go through to figure out what our W's are. In this case, in a linear regression, right, it's like you square the sum of the errors, you sum the square of the errors, right? And so that's, how we would do it in the regression. But this is, if you think about it, this is kind of like a generalized way, right? So the W's, they could be calculated in the same ways as the betas. But as we generalize our neural network, we'll find that the way that we calibrate the weights don't always have to be in this like sum the square error part. So the I's are arranged as these tensors. Okay. So scalar is a 0-dimensional tensor. A vector is a 1-dimensional, a 1D tensor. Matrix is a 2D tensor. And then an array is an n-dimensional tensor. So we refer to tensor as like these inputs that can be of different dimensions. Okay? Any questions? So, just as a quick reminder, right, so solving for betas versus W's. So this was actually something that I had brought up earlier on in the class when we were talking about linear regressions. So in a linear regression, it so happens that the optimization to minimize those squared errors with respect to changing our betas is or has a analytical solution, right? Which means that I don't have to run it through some kind of optimization algorithm. There's actually an equation that I can just use to solve for the betas. Does anyone happen to know what that equation is or remember? I guess we're all tired today. Beta is equal to xtx inverse times xty. Okay? So this equation allows us to solve kind of instantaneously for the betas. This is how it works when you use the ln function in R to solve for your betas. It is closed form analytical solution. Guaranteed the correct solution. And fast parentheses in theory. So you don't have to solve for betas in using this equation. You can actually solve for them in a slightly different way. And so if you guys remember from that earlier lecture, one of the things that I was saying is that actually in a lot of machine learning applications that solve for the weights in like a linear regression, they don't do this, right? Because this neural network is like a generalized form, and actually you can apply certain algorithms to solve for the weights in a more generic way. But when you do that, you can't have like a closed form analytical solution for everything, right? But it turns out that when you do it, I guess an additional reason why it's not done this way sometimes is because even though it's fast in theory, if you have a lot of data, that -1 taking the inverse of a really, really large matrix is super memory intensive. And that can actually kind of crash your ability to solve for the betas. If you have like, let's say, 100,000 variables or 1 million variables or something like that, it can be very difficult to compute that matrix. And so in this case, so weights are obtained by solving numerically through optimizers such as gradient descent. Okay, so this is not nearly as memory intense as analytical. Can scale efficiently. So if you're doing gradient descent for 1,000 variables versus 100,000 variables versus 10 million variables, it can actually still be very efficient. And can be applied flexibly. Not to just linear forms. Okay. So let me kind of draw a diagram here to maybe describe this. So we have some input, and this may be transformed in a layer. And you may do this several times. This will generate you some predictions. I can think about predictions versus true values. And have some kind of loss function. Oops. Maybe this generates a loss score. Okay. Before I kind of continue on here. So loss function as a description of like a comparison between predictions and true values. Okay? So we've been doing this a lot, right? So you generate a model, you have the model predict values for you, and you compare it against true values. So what is this procedure called? What was that?
Regression.
No, the regression is like the whole thing, right? What is it called when I'm comparing true values versus predicted values? And why would I be doing that?
Validation.
Yeah, validation, right? So the whole point is my model gives me some values. How can I tell if the values are any good? I compare them against the true values. Okay. And so your loss function is a comparison between these two things, and so this might be your y hat minus y. And your loss score is a measurement that like quantifies all of that loss, or how good the whole thing is. So does anyone know what we have been using in this class as our loss score? Yes, perfect. Mean squared error is probably the most common loss score that is used. It's not the only one, but you know, it's the one that we've been using in class. It's a very standard loss score for most of these types of models. Okay? And the whole idea is that I can take my loss score, feed it into some optimizer, and there are these weights. So then this is my weight update. Okay. So we are thinking kind of theoretically, qualitatively about how this works, right? So if I have a loss score, that happened because, okay, I have weights, or in other words, betas, right? So betas are going in, they're transforming my input until I generate some predictions, I generate the loss function and the score, and then it tells this optimizer, okay, so like, so what does it mean when a MSE is really large, generically?
Your predictions were very far away from the true value.
Yeah, exactly, and so it's like, So then so it tells like, hey, you did a bad job, and the optimizer says to the weights, okay, please change and do better. And then it goes through this whole thing again, and then maybe the MSE decrease a little bit, and it's like, okay, good job, keep going, right? And so change the weights, gets better, so you have better predictions, you have a lower loss score, and it's gonna keep doing this until it's gotten to a point where the loss score it's unable to change the loss score, right? Or you've like reached like an acceptable sort of threshold for your loss score, okay? So like principally, this is kind of what we've been doing in many different ways, right? There are, so, okay, let me think. So, in the stepwise regression, right, we can change the weights, we can change the betas, and then there's an additional thing that we can kind of mess with to have the model fit the data in different ways. And so what was that one parameter? Does anyone remember for stepwise regression? It's the number and location of your breakpoints, right, in a stepwise regression. In a polynomial regression, it is the number of polynomials that we have. In a spline, it can be, in like a natural spline, right, it can be the number of polynomials, although generally we just do 3, and it can be the number and location of the knots, right? In the natural spline, or the smoothing spline, it's the tuning parameter, right? So, all of those things that I'm talking about are like flexibilities in the model to give us predictions in different ways, and then we kind of re-optimize, right? And we've been doing that via cross-validation, which is essentially a procedure to tell your optimizer to like make a better selection of the tuning parameter, or the number of knots, or the breakpoints, or the number of polynomials, okay? Okay, I can't tell if you guys are following me. So that kind of analogy in machine learning is they've kind of honed in on specific things that you can be flexible on. And those things are, so yes, the betas, right, are weights. You know, you want to alter the betas in such a way that you can get the best predictions possible. But there's also two things which we're going to talk about. So the number of layers, so how many times this happens, and the type of transformation. And those are the things that are adding flexibility into the model, right? And when I'm saying flexibility, right, you guys remember that I talk about this, like the wiggliness of the line, right? And some of the earlier things that we talked about, the number of polynomials is what gives wiggliness to the line. The tuning parameter of the knots is what gives ability for the line to be more and more wiggly, right? And so the thing that is happening in these neural networks that gives you that ability is number of layers, and what we're doing the transformations into. Okay. So let me let's take a step forward here. What is this? So I'm going to write out that linear regression equation again, the machine learning version, and we're going to change it just a little bit. Okay, so we're going to have, once again, I1, I2, we're gonna go like this, and an L, W11, W12. Okay, so we can do a new function, F2, I1, I2. This is equal to W11, I1 plus W12, I2 equals L, but I'm going to do one extra little step, which is I'm gonna have, not multiply, it's gonna be a function A. So A is the activation function. And this allows for a non-linear transformation. What's happening? Hello? Alright, I guess we're not writing anymore. I don't know if I just messed up some setting here. Okay, we're just gonna start on a new sheet. Okay, so sorry, let me rewrite this. So F2, I1, I2 is equal to A, W11, I1 plus W12, I2 equals L. A is the activation function, and this allows for non-linear transformation of the inputs at each node. Okay, so basically the idea is we can flexibly alter the functional form with a generalized activation function A. And so let me walk through a couple of different activation functions, common activation functions. So common activation functions. So there is the identity slash linear activation function. So this looks something like f of x is equal to x, okay? So we have this linear model and it remains linear, okay? So that's kind of the most straightforward one. The activation function is just in the same functional form that you put it in, which in this case we have as linear. Okay, so step slash, oh, out of batteries. lot of technical difficulties today. Okay, so step slash binary step, or binary, not binary step. So this is an activation function that does this. So f of x is equal to 0 for x is less than 0, and 1 for x is greater than or equal to 1. So in this case, we would get something like this. So 1, 0, 0. We would see a line that goes like so, step up, and go like that. Yes?
Would it be 1 for x is greater than or equal to 0 or 1?
Oh, yes, sorry. Good catch. This will be greater than or equal to 0. Yes. So this basically transforms you from 0 below something and then 1 above some kind of threshold, right? So this might be something that you would use for like mapping outcomes to binary outcomes, for example, or discrete outcomes. Okay. So hopefully these are things that are kind of familiar. So logistic. So this is an activation function f of x equals 1 over 1 plus e to the negative x. So this is 0, this would be 1, and you would get something like a sigmoidal curve that looks like this. So that's logistic. We've got another common one is called tan h. This is f of x is equal to e of x minus e to the negative x divided by e to the x plus e to the negative x. And this one is going to be somewhat similar. So we have negative 1, 1. So this one is also sigmoidal, except that it passes through at 0 as opposed to 0.5. And the last one is known as the rectified linear units, also known as ReLU. So this is f of x is equal to 0 for x less than or equal to 0, x for x is greater than 0. And this one looks like this. So 1 up to 0, and then okay. So there's lots of different activation functions, right? We've talked about identity, step, logistic, 10H, and ReLU. And I kind of view this in a similar way with splines, right? So flexibility afforded by different activation functions is one way that we can add the squiggliness into our model. But remember with splines, you have a choice of messing with the number of polynomials, and you also have a choice with messing with the number of the location of the knots, right? And it just so happens that most people end up leaving it's too many degrees of freedom, right? So most people just leave the number of polynomials to 3, so it's usually cubic splines, and then they mess with the knots. And to some degree, that's kind of true here as well. So a lot of people actually tend to use the rectified linear unit, the ReLU, as kind of the, I would almost say default choice, although I should be careful because, you know, these activation functions, there is something about trying to make sure the context of your problem, of the data, and of your outcomes are kind of sensibly done with respect to the activation function. But kind of at the end of the day, especially when you're dealing with like continuous models, ReLU is kind of the thing that most people will at least start with, if not default to. One of the reasons for this, we won't get into a huge amount of detail. It actually has to do with the computational ability of models to handle what's known as, it's called a vanishing gradient. So it's like in the algorithm when it's trying to solve the problem, in pretty complex problems, there's this issue where in optimization models, if you're doing something like a gradient descent type of algorithm, so the way that you can think about this is, like if I'm trying to find the lowest point in a curve, right, I can start at a certain point and move in a direction, move down a gradient, right? If I take a step in a direction, right, based off of like the derivative of that function, I can like make my way down until I hit some kind of minimum. That's how these models work. And a rectified linear unit helps to solve a problem where you have what's known as a vanishing gradient. Okay, so you don't have to know the sort of details about that, but I'll just say, yeah.
Question, what is the closed form?
Okay, so closed form means closed form or an analytical solution. Okay, I guess I didn't really define that. So you can have analytical, so this is closed form, versus numerical. Okay, so ten x squared plus 5x minus 2 is equal to 0. Okay, so if I ask you to solve for x, how would you do it? Does anyone remember this from high school? I'm realizing that I don't remember the quadratic formula at all. It's like, what is it? It's like, there's like 4 AC or something.
X equals negative b.
Well, sorry, say it.
X equals negative b plus or minus the square root of a squared minus 4ac
Yeah.
all over 2a.
That is super
Or
impressive.
is it b squared?
B squared
Yeah.
B squared minus
Sorry.
4ac.
Yeah. You gotta sing the song.
I was not taught this song. Okay. So this right here was derived somehow. Some mathematician proved this, right? This works for all equations of that form, okay? But it's specific to that problem. It's a closed form solution. I can just plug numbers in and get the answer. There's other ways I could solve for this, right? So I could just x equals 1, then let's say this is y, then y equals something. Is it? No. Okay. X equals 2. Y equals what? Okay, so numeric is like guessing and checking. But it's guessing and checking in like a smart way. There's like algorithms that like check these things in certain ways. And so closed form solution. So the analog of this for what I'm talking about in the linear regression, the closed form solution, right, for our betas was this thing, xtx minus 1. This is xty. So this is the same thing as my quadratic formula, but where I'm solving for the betas. Okay, so that's closed form. Numerical would be like a gradient descent algorithm. And this will let you solve for the parameters in a way where essentially I'm like guessing and checking in a very like specific way that allows me to arrive at the best answer. Yeah.
That leads to question number 2. When
Yeah.
you say that the model has the ability to handle vanishing gradient,
Yes.
I mean that
Relu, yeah.
because this might give like false dips in multi-dimensions. So it could be like the false minimum, and this can tell.
No, that's a different problem. That is, that has to do with non-convexity. Yeah, that's different issue. It is an issue in some sorts of models. These are designed, these activation functions avoid that because the choice of the function is going to not, they purposely choose convex functions so that you don't run into that problem. But
So it's just one solution.
for example, okay, like one issue that you could deal with is, oh my gosh, so let's say you want to you want to find the minimum of this function here. If I start here, and I take a really big step. So, okay, so the way this works, right, is I'm the optimizer. I start at a point, I'm like on a hill, and I inspect the gradients, and the way I do that is I look in all directions and I see which way is down. And then the next step is, well, what do you guys think the next step is? I take one step in the down direction, and then I check again. I look everywhere, and so what you want to happen is something like this, here, this, here, and so on until you get to here. when you're at the bottom, you look in all directions and you see everywhere is uphill, and you're like, okay, great, I'm in the right spot. Okay, but you could take a step too far, right? In which case I might go all the way here. Okay, and maybe that's okay because now you go in the other direction, and maybe you take a step too far, and so on and so forth. So you want to avoid taking steps that are too big because you'll kind of bounce back and forth. It might take a really long time, and in fact, in some cases, you'll never get to the right spot. That's kind of rare for that to happen. But hopefully you guys can see that the size of the step that I take in a direction matters, right? So then what if the hill looks like this? Okay. And my point is all the way up here. So now I kind of look around and I don't really see a good gradient. Maybe there's like a very slight gradient and I might take a step, right? And so there are aspects of the way that the problem is structured that may make it really difficult for you to solve certain types of gradients, right? And so this is like one example. And so we're not really covering into some of those aspects, and so yeah, it'll get maybe a little more theoretical than what we have time to get into in this class. And so basically all I'm saying here is that it turns out that the rectified linear unit happens to avoid common problems with solving for the weights that you might see in other activation functions. Make sense to everyone? Hopefully. Okay. So now let's think about a full-on, maybe more complicated neural network. We're going to look at something called a feed-forward neural network. Feed-forward neural network. And so this is a multi-layer perceptron. So I1, I2, this will go to L1, L2, L3, P. It's gonna start getting a little bit messier here. Okay. And now I'm going to label the weights. So this is W11, W21, and W31. So the numbers refer to, the first one refers to the node that it's going to. So W1 going to L1, W2 going to L2, W3 going to L3, and then the second number refers to the node that it's coming from. So I1 is W11, I1 is W21, I1 is W31, okay? Which would make, so how would I label these three lines? Yep, W12, W22, and then W32. Perfect. And you add the dimensions kind of like right to left. In this case, this would be V1, V2, V3. Because if you had, just to be consistent, if you had P1 here, this would be V11, V12, and V13. Okay, we'll leave that out. Okay, and I can generically represent the equations of this neural network like so. So this would be L1 is equal to, actually, can you guys tell me what this would be? What would L1 be equal to?
I1,
Okay,
W11
yeah, so W11, I1,
plus W12, I2.
yep, perfect. And you have two inputs into L1. Great. One more thing. What are we missing?
Minus B1B.
No, we're just looking at L1, so we haven't gotten anything about P yet. We can also apply a what to this? What was the last thing we looked at? Yeah, the activation function. It doesn't have to be ReLU, but so this would be A11 like so. Okay? Which would make this something like L2 is equal to A12 W21 I1 plus W22 I2 L3 is equal to A13 W31 I1 plus W32 I2. And then here, this guy would be P is equal to A2 V1 L1 plus V2 L2 plus V3 L3. How's everyone doing so far? So this it's looks a little bit complicated, right? But essentially we are doing these kind of several regressions that have some kind of transformation, and you're doing it like a couple different times, so that you're essentially adding lots and lots of flexibility into the model, and so that the parameter can functionally fit to many different sort of forms.
Can you explain the nomenclature for the A subscripts?
Yeah.
Like, why does P have A2,
Mm-hmm.
but that the rest of them have some?
Yes. this layer 2, and this will be layer 3. And actually layer 2 is known as a hidden layer. Okay. So all it is nomenclature for, oh actually I guess this would be layer 0, layer 1, layer 2. Okay, so there are 3 different activation functions in layer 1. And so A1, A11, A12, and A13, where the first one just refers to the layer that it's in, right? And so here it's just layer 2, and then there's one indice telling you which one of those 3. Yeah.
If there had been like multiple P's in there too.
Mm-hmm. Yeah, so if you had a P1 and a P2 and they went into it like this, then you would have A21 and A22 for V1 L1 plus V2 L2 plus V3 L3. Make sense? Okay. So in like a simple linear regression, right, it would just be my IQs going into a single output, right? But because I've set it up in this way, you can have a whole bunch of different, you're allowing a whole bunch of sort of transformations to happen. So this would be equivalent to, okay, if I were to use our kind of old notation, it would be like beta 1 x1 plus beta 2 x2 equals something like a, or let me use a different thing, would be equal to, let's say e, beta 1 x1, or beta 3 x1 plus beta 4 x, oh my gosh, x2 equals f, beta 5 x1 plus beta 6 x2 equals g, and then I would have something like y is equal to alpha e, alpha 1e plus alpha 2f plus alpha 3g. And then I could run the model, calibrate all this stuff, calibrate my beta 1 through beta 6 and my alpha 1 through alpha 3, and then I could do my y hat minus y and my MSE and all that, and then I would be recalibrating many different betas. Okay. So in the linear regression, you're taking like 2 inputs and you're getting 2 parameter values. But here, it's a lot more, right? And so that's what gives a lot of flexibility to the model, and this isn't even including my activation function yet, right? And so these can actually even be transformed even farther. So I am introducing flexibility into my model by doing this. And the flexibility is related to the number of nodes, EFG, right? And the number of layers, like here and here. So when I talk about adding flexibility into the model, you're increasing model complexity, you add more wiggliness, right, into your functional fit. When does it become too wiggly? And how do we know that? How have we been dealing with that in this class so far?
False.
Well, you could plot it in some version, but some you're not going to be able to visualize so easily. So what do we do?
A summary table?
Hmm?
A summary table?
Not quite. So if we are, yeah, how do we know that we've gone too far into like overfitting territory? And how do we avoid that? No ideas? I've asked this question many, many times.
Cross-validation.
Cross-validation, right? So cross-validation tells us how much flexibility to add into the model. And it tells us when we've added too much flexibility into the model. And so how do we add flexibility in a neural network? What are the two things?
Layers.
Layers and number of nodes. Okay. So cross-validation, and the activation function. So activation function, number of layers, number of nodes or perceptrons. The node is a perceptron. So it's a little tricky, right? Because cross-validation, usually we've been dealing with like a tuning parameter is too low or a tuning parameter is too high, or just like some set number of polynomials you can do low versus high versus medium, whatever. But now we've got like many different things that we could vary. So you do want to do cross-validation, but there are some general rules of thumb that people use when they start figuring out how many layers to add, how many hidden layers to add, and how many nodes to add. Okay. So how many hidden layers and nodes / perceptrons. Okay, so rough kind of rule of thumb to kind of get you started here. So number of hidden layers generally. 0 represents linearly separable functions. 1 approximates any continuous mapping in finite space. right? So very powerful. So think about this, right? With a single hidden layer, I can map any functional shape that is continuous. And then 2 plus represents arbitrary decision boundaries. To arbitrary accuracy. With the correct activation function. So it is possible to map any function if you're using to a good degree of accuracy if you're using the correct activation function with even 2 hidden layers. Yeah.
The only case I can think of for 2 plus is like human decisions that could be seemingly random or too complicated to understand. What do you use it?
Yeah, I mean, I think it's more meant to represent like non-continuous mapping. Yeah. We're thinking of like something representable in data, right? So oftentimes you'll want to do multiple hidden layers if you are representing discrete outcomes, but not always. If it's simple enough, you could sometimes be able to do that in with just a single hidden layer.
Just an example of it, not to make it from scratch, but something that was modeled in this way.
Yeah, we're gonna look at an example in a second. Okay. Number of nodes / perceptrons. So no agreed upon metric, so this is rules of thumb, and they're not all the same. So size of input layer is greater than hidden nodes is greater than size of output. Another different one that people use, hidden nodes, is 2/3 input plus output layer sizes. And a different one that people use, hidden nodes, is less than 2x the input size. And last one, hidden nodes is equal to number of samples divided by alpha times number of inputs plus number of outputs. So if you have one output, 100 inputs, and let's say your sample is like 10,000 data points, then number of hidden nodes is, so okay, alpha is usually between 2 to 10. So, you know, if you had something like 10,000 rows divided by, let's say, 10 times 101, so this would be approximately 10 hidden nodes as a starting point. Okay, and so more nodes is overfitting, and so this might be one of the ones that you could hone in on with cross-validation, is selecting the correct number of nodes for your model. Okay. Questions? Okay, so let's jump over to R. And maybe this can help with kind of understanding an application of a neural network. So we're going to use a couple libraries, ISLR, that we've used before, data table, ggplot, and we're also going to need a library called neural net. Oh, yeah.
So on this one, it's kind of clear that you have like the first layer, second hidden layer, and then the output. Can we say one of those layers are the like input variables, and the other can be control variables, and then outcome, or there's no relationship? Like
Your explanatory variables on your left, and your response variable is on the right. And everything, every layer in between that is a hidden layer.
Would those be control?
I don't know what that would mean. What is a control variable?
And what I understand is the ones that may affect how the input variables interact. Like
No, so a hidden layer is some transformation of your inputs into some random thing, right? And so actually, like, one of the things to remember, this isn't answering your question, but one thing that I did want to mention, right? So we're talking about like applying all of this stuff into a neural network. So you have beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, alpha 1, alpha 2, alpha 3, and then the form of your equation is also transformed by your activation function, right? So we are like so solidly in the prediction area and not in the inference area, right? Because none of these betas are interpretable in any way that would let you translate something from an input to an output like a linear regression would, right? Because in a linear regression we say, oh, beta is the slope, and so as x changes by some amount, then y changes by some amount. Okay, that's easy enough, but you can't do that here, right? X changes by some amount, and then that's going to affect E, F, and G, depending on the activation function, which then all roll into something over on the other layer, the transform that then is transformed and then gives you your y output, right? And so if I said, okay, you know beta 1 as x1 changes by 10 units, how does y change? I have no idea, right? Like it's
does
very
answer the question.
okay. Oh yeah, okay. Yeah, so okay. Yeah, so E, F, and G is like your hidden layer, and then you like transform it again. Alright, we're gonna use dataset defaults. Gotta load the libraries first. So this is a dataset from ISLR. I'm gonna put it into a data table. And let's take a quick peek at this data. 10,000 observations with 4 variables. Default, yes or no, did you default on alone? A variable for whether or not they're students, a variable for their bank balance, and then a variable for what the income is. And so, pretty simple model. We want to see whether or not someone, we want to figure out if we can predict whether or not someone is going to default on a loan based on whether they're a student, based on their balance and bank balance, and based on their income. Okay. Okay. Okay, I'm actually gonna copy and paste some stuff here. And let me walk through what I'm copy and pasting. So I'm gonna change the yes and no for the default variable to ones and zeros. So default as numeric, I'm gonna create I'm gonna modify the column to now become numeric. It will say 1 if it's yes and 0 otherwise, and I'm gonna do the same thing for whether or not they're students. It's gonna be 1 if it's yes and 0 otherwise. Okay, I'm also going to scale the data. This is generally a good practice to do. It makes the computation of these things a little bit more robust. So everything gets scaled. And then I'm going to sort the data. And split it into a training set and a testing set. And it's done in such a way that 70% of the data is going to be trained on, and then 30% of the data is going to be my test set. And so that's what I'm going to do that's what I can use to measure measurements of my loss function, and my loss score is going to be against the out of sample test data. Yeah.
How you scale the data? You take the variable you want to analyze.
Oh no, there's actually a function called scale, which will look at whatever I want it to be, whatever things I want to be scaled, which are going to be my 3 explanatory variables, and it's going to normalize them essentially, or scale them so that they're in the same range of values.
Okay.
Yeah. Okay. So default neural network. So we're going to use neural net, and I'm going to do same as always. Y variable regressed on all of my other variables. The data is going to be from default.train. I am going to use, so hidden refers to the layers, and then you have to tell it how many nodes in each layer. So I'm going to do 2 and 3. I'm just picking randomly. My activation function is going to be a logistic, and the reason why I'm choosing logistic is because my outcome variable is 0s and 1s, right? It's you default or you don't default. Linear output is equal to false. Okay, great. So I didn't run all of this stuff, right? Okay, one sec. Run. Okay. So it did something. So I can look at the summary, and this will give me a bunch of information about the model that I can go in and look at, right? I think I can do something like default.nn $weights. So this would be grabbing the solved weights, the W11, W12, W13, and so on. And you get all of these back. Don't know how useful this is, again, right? Because we care more about prediction. but I can do something like this. I can plot the neural network. And let me okay. So this is the solved neural network, and these things, these values are the weights for everything, and you could like manually go in and plug this in, and so you figured out you could plug in individual data points to predict what the outcome would be with the solved weights or the solved betas. Okay, so we can now predict based on our test data and see how well it does. Okay, so predict, and if I click here, how do I look at this again? The net results, I think, is what I want to look at.
The icon next to the list of length, and then on that thing.
Sorry, what was that?
The icon next to that number will show you in the other column. Yeah.
Here?
Yeah.
Ah, yes, okay. So I can do like dollar net result or something. Okay, anyways. In a logistic, remember the output is probabilities. So these are probabilities that somebody defaults. So we can say something like they'll default if the probability is larger. Yeah, okay, so this is how we look at the results. Or I'm adding it as a column. And then I'm going to create another column called predict if the probability is greater than 0.5. Okay, so default test. Okay, so this is my test data set, the 30% of the data that I left out. And then these are the Y's. These are the probability that the model thinks that it's gonna be defaulted. This is the output, the predicted output. So this is like my Y hat essentially. And then I created a new column that said if it's greater than 0.5, then you can predict 1. Then you would predict that they did default. Okay, so the overall MSE is the sum default dot test dollar default minus default dot test dollar predict. So I'm manually calculating the MSE. Okay. So our model has an error rate of 3%. So in 97% of the predictions that the model is making, It is correctly identifying someone as either defaulting or not defaulting. Okay? And so, yeah, this is kind of the, let's say, bread and butter of what you would be doing in some kind of prediction model, and then figuring out how good it is by comparing it against the test data. So who thinks that that's pretty good, 3% error rate?
Yeah.
Is there any nuance that we need to think about here?
The level of debt.
Huh?
Level of debt.
No, if we're just talking about whether or not they default. So, let's say there's 100 people, and of those 100 people, 3 people defaulted. So if I guess that everyone didn't default, how many would I guess incorrectly?
You said.
So
Guessing that no.
there's 100 people,
Yeah,
3 of the 100 people defaulted,
yeah.
and I'm just gonna do a prediction for the 100 people. I'm just gonna say nobody defaulted.
Right.
What's the error rate of my prediction? 3%. How many people how many people actually defaulted when I didn't say they defaulted? What's the error rate there? 100%. I incorrectly guessed everyone who actually defaulted. So even though my error rate is really low, it actually kind of depends on like how many people defaulted, right? Because if that number is really low, I could just like guess that everyone is not going to default. So what is that number? So let's take a look. So how would I do that? So sum default dot test dollar default, right? Because it's 1 if they did, divided by n row default dot test. Interesting. So 3.6% of the population, only 3.6% of the population defaulted. And so here, maybe this is not as good as people think, right? With a 3% error rate. So we can look at that, right? So we can have a false negative rate, and we can have a false positive rate. So false negative would be you defaulted. Well, I think you defaulted even when you didn't. And I can do it like this. It's the same thing except I have an if-else statement to qualify whenever it's directional for the error. So if test default in the actual one is bigger than the predicted one, that would be a false negative. Okay, so how often do I guess someone's defaulting when they don't default? Very low, only 2.5% of the time. But how often do I guess that they didn't default when they actually did? Oh wait, other way around. Oh, sorry. Okay, yeah, I had that opposite. So your false positive rate is a lot lower than your false negative rate. So false negative being you incorrectly classified a negative outcome. So these can be really different. Your error rates can be really different. Okay. Questions about that? Okay, we definitely don't have time to do convolutional neural networks, but maybe we can close out with that next time. So that's going to be a particular application of neural networks as it relates to, actually, so it doesn't have to be, but a commonly used way of actually doing classification on images, okay? And so, yeah, think about that for a second. Like, we've been dealing with numbers and tables all the time. How in the world are we gonna do something with pictures? Okay, and so this will be a pretty nifty application of neural networks as applied to something like pictures, and we'll round out the class with convolutional networks and a summary of everything that we've covered. We'll do that next time. Okay, that's it for today.